There we go. All right, so I need this, and we need this, and we need this, and this. All right. So guys, grab your books, and we may as well just lay them open to the page that we're going to need. I don't know. Josiah Willard Gibbs. He's a good-looking fellow. 809. So guys, we in a moment are going to transition down to the bottom of page 809 and look at that table 19.3. I'm going to project it on the screen, but you're going to see that from a distance it's hard to see the details. So you're going to be a lot happier looking at it in your book. You guys ready to go? Okay. So guys, you've already got all of this in your notes. So here's what we know. We understand that we've got some competing realities. We understand that we care about spontaneity. We understand that thermodynamically there are two quantities that lead towards a reaction being spontaneous. As we said in chapter 5, reactions that are exothermic tend to be spontaneous. As we said in chapter 19, reactions that increase entropy tend to be spontaneous. But guys, there are times where that can create tension. We have offsetting changes taking place, and we need to be able to determine definitively, is a reaction spontaneous? So to do that, we've got to bring enthalpy and entropy together, and that happens through our good friend Gibbs, who came up with this concept of free energy. And so the idea here is that we have this simple representation that says a change in Gibbs free energy is equivalent to a change in enthalpy minus temperature times the change in entropy. And then guys, we said these three significant things. If we do that math, and if delta G is negative, that reaction will always be spontaneous. It is giving off Gibbs free energy. It will always be spontaneous. Delta G is 0. That reaction is at equilibrium. It is going both directions simultaneously. And then finally, if delta G is positive, the process that represents is never spontaneous, but the reverse process is always spontaneous. How you doing? Questions about all of that, guys, was review from last time. You're good? Okay. So, guys, let's put a little bit finer point on this. And, I mean, it's sort of conversational, but if you want to write it down, you can. Guys, when you think about Gibbs free energy, the problem is that entropy, for many of us, is rather sort of abstract. So, if Gibbs free energy contains, the concept of entropy, how do we sort of conceptualize this? And guys, for me, it's helpful to go back to what we said at the very, very beginning. We understand that balls roll downhill. We understand that eggs go splat. We understand that nails rust because they are releasing energy. And now, guys, we're ready to actually say it in a way that is really always true. And it's simply this. Anything that happens releases energy. What kind of energy? Gibbs free energy. And so guys, when we understand it in that context, we can then say this, and this is worth writing down. In any spontaneous process, free energy is always decreased. Every time. And it does make sense mathematically. So guys, what we then need to talk about is that there's a couple ways that we can actually measure free energy. We've already got one, delta G is equal to delta H minus T delta S. But guys, we can also do this. We can actually also calculate free energy changes in processes through the third of these equations on the page 4 side of our super duper handy dandy AP equation sheet. This is actually the fourth equation on there. And guys, it looks just like the others. Final minus initial, products minus reactants. And by looking up delta G values, which, yeah, are back in Appendix C at the end of the book, you will find out that you can calculate Gibbs free energy values by looking at the change in Gibbs free energy when the products fall apart, looking at the change in Gibbs free energy when the reactants form, subtracting one from the other, and you can come up with delta G values for reactions. You good? Yeah?
So is Gibbs free energy it's similar to enthalpy, where we can't measure enthalpy in and of itself, but we can measure change in.
That's correct. Exactly. Yeah. Yeah. So
measure specific Gibbs free energy here, but we can measure the change.
Exact. Precisely. Yes. Yep. Good point. So guys, this then becomes an interesting question. So we've got this way of calculating delta G, but we also have delta G is equal to delta H minus T delta S. So guys, which one of these are we going to use in order to calculate delta G values for reactions? Depends on what you're given. If you are given a table of delta G's of formation, you'll use the top one. If you're given some enthalpy and entropy data, you'll use the bottom one. And actually in homework today, Rebecca, was it you and I that was talking about this before the weekend? In homework today, you're actually, for one reaction, going to do both, and you're going to find out that you get exactly the same answers. So they will give you both sets of data. They'll give you some, well, you'll go get formation data out of Appendix C. You'll come up with delta G. Then you'll actually get the enthalpy and entropy data, also calculate delta G, and you're going to find out they do work out to be exactly the same. So as we said, the one that you'll choose is the one that's easiest given what you're given. Yeah? Yeah, well, but within... Was it you and I that talked about this?
We didn't talk. Well, you mentioned it to me up there, but
okay.
I went and did it.
You went and looked at it. Okay. Yeah, so they're within significant digits. They're the same. Yeah. Okay. So guys, you comfortable with it? All right. So let's do this, and then let's transfer into the last big idea. So we talked about the idea of spontaneity. What you're going to find out is that in a bunch of months, we're going to tie this into equilibrium. So we need to say this as well. It's not a contradiction or a new idea. It's a new way of thinking about something. And guys, it says this. If delta G is less than 0, if it's negative, the reaction favors products. And if it's greater than 0, the reaction favors reactants. So I'll show you what that means. Because again, it's nothing new. But let's make sure you're clear on what this means. So guys, we understand that in a reaction, we can think of this as reactants turning into products. So what does it mean if it says delta G is less than 0? Well, delta G is negative, right? So what do you know from the previous page of notes? What do you know about reactions that have negative delta G values? They're spontaneous. That means reactants turn into products. We could say they favor products. Now, what if it's positive? Remember what it said at the bottom of the other slide. If delta G is positive, what does that mean? The forward reaction is not spontaneous, but the reverse is, simply meaning that this reaction favors reactants rather than products. So guys, it's just another way of thinking about what was on the previous page. You okay? All right. So guys, now we are ready to wrap up the unit, and it goes like this. We are now ready to look at the interplay of enthalpy and entropy, and finally, definitively say that reaction's spontaneous and that one's not, and under what conditions they are spontaneous. So guys, the conversation goes like this. So here we've got our Gibbs free energy equation. Let's make sure that we understand our terms. So guys, delta G is free energy. Delta H is enthalpy. Delta S is entropy. Got it. T is temperature. Okay. Mm-hmm.
So it's temperature times entropy.
Yes, temperature, yes. So what you're going to find out, though, and I'm glad that you mentioned that we consider this entire term to be our entropy term. So we understand that delta S is entropy, but we also understand that disorder is affected by temperature. And what you're also going to find out is that this is a subtractive relationship, and you'll see why in a minute. So we consider that entire negative T delta S to be our entropy term, and you'll see why in a second. Yeah.
So, like if someone were to ask me the question, hey, well, the AP test or something like that, what is the entropy term? I wouldn't just say delta S, I would say
Well,
negative.
what is the abbreviation for entropy? S, or delta S if it's changed. But in the Gibbs free energy equation, what represents the entropy of the system? And that would be the negative T delta S. Okay, so guys, let's call time out for a second, and we're going to kind of turn this into a game. It's not a very fun game, but most things we do in chemistry aren't. So this is as good as chemistry games get. Okay, so guys, we're going to turn this into a little bit of a game. And this game is going to be the battle between good and evil. Okay, you ready? I know. Ooh, yeah, it's sort of like the first 4 chapters of Genesis. So guys, we've got this battle between good and evil, and here are the underlying ideas behind the game. I don't know why, but something in this lab, do you guys smell that? Something's weird. I gotta shut. Okay, so guys, these are the rules for the game, but let's actually make sure you understand what this game is all about. Guys, what we're gonna do is we're gonna figure out if reactions are spontaneous, okay? That's the big picture, the end of chapter 19. So here's the idea. Big question. Is this reaction spontaneous? We're going to turn that into a battle between good and evil. Okay? Now, here's the idea. Spontaneous is good. Okay? Non-spontaneous is bad. Now, guys, please, for the love of all that's good, when you take the AP test, please do not write down this reaction is good. Okay? It's this reaction is spontaneous. Typically, you won't do that on the AP test, but you will on the unit test you're going to take next Monday. So guys, the big idea, no, you shouldn't. If you do, it's wrong. No, don't do that. Okay, but guys, for our reasoning here, spontaneous is good, non-spontaneous is bad. You get the idea? Okay, so with that in mind, let's talk a little bit about this equation just to set the stage. So guys, we understand now that the final predictor of spontaneity is Gibbs free energy. You guys sold on that? Okay, so, and we'll use the terminology as we develop this. So guys, what delta G values indicate a reaction is spontaneous? Negative. So guys, what that means is negative delta G values are good. Get the idea? We're going to use good instead of spontaneous. Now guys, if negative delta G values are good, now let's talk about enthalpy, heat going out or coming in. Guys, what kind of reactions tend to be spontaneous relative to enthalpy, endo or exothermic? Exothermic. What is the sign for what is the delta H sign for an exothermic reaction? Negative. So relative to enthalpy, negative is good. Got the idea? Okay, now guys, what about entropy? What types of reactions tend to be spontaneous? Ones where entropy goes up or ones where entropy goes down? Where they go up, and so in terms of sign, which one is good for entropy, positive or negative? Positive, because entropy is going up. You get the idea? Okay, so now guys, we need to define some baseline ideas. So it goes like this. This is all just review, but you may want to write it down. We understand that Gibbs free energy is the sum of an enthalpy term and an entropy term. So you're going, wait, this isn't a sum because this is subtraction. But guys, you should be comfortable with the idea that subtraction is really just adding a negative number. Okay, so here's the way this goes. Enthalpy can either be endo or exothermic. If it's positive, it's endothermic. If it's negative, it's exothermic. Now guys, circle the one of those two. Well, I'll tell you, and then you can do it as you catch up. Circle the one of those two that's good. Which one's good? The positive or the negative? Which one's good? Which one's good? The negative one, right? The second one, exothermic. And again, good means spontaneous. I got you. Okay. Then, guys, enthalpy. So this is where this gets a little bit interesting, and this is what Talmage mentioned. Guys, or I'm sorry, not enthalpy, entropy. So, guys, the idea is this, that our entropy term is the whole second half of this equation, negative T delta S. So what we find out is that entropy is dependent upon temperature. And when we say absolute temperature, what does that mean our units are? Kelvin. So, and maybe we should have a little aside and think about that. Guys, why is it important that this is related to Kelvin temperature? So, yeah, you can't ever be negative. Good. So Kelvin can never be negative, and that makes the math always work out. But guys, what is then the concept behind it? Think about this. If temperature goes to 0 Kelvin, what does the value of this become regardless of what delta S is? 0. What does that mean happens to a substance at absolute 0? Entropy becomes 0. So guys, what does that mean happens to disorder at absolute 0? Becomes 0. Guys, it's actually the definition of absolute 0. Absolute 0, they actually define as the temperature at which a substance is perfectly ordered. There's no disorder. But doesn't that make sense? That if you get something cold enough, certainly that thing is going to be locked into a crystalline structure. So we lose the disorder of the macro movement of the particles. So then these particles are locked in place. And what then gives them any sort of disorder? Simply their vibrations. And at 0 Kelvin, they stop vibrating and their entropy falls to 0, meaning they are perfectly ordered. Does that make sense? Kind of crazy, right? Okay. So, guys, how then does this play out relative to the math? Well, guys, also, and this is what Rachel pointed out, that T is always going to be positive. Because it's Kelvin temperature, T is always going to be positive. So, guys, now this is where this math gets a little bit interesting. So let's talk about it, and then I'll give it to you in note form. So, what is going to happen to the value of our entire entropy term if delta S is positive? And let's talk about it. What does positive delta S mean? What's happening to entropy? It's going up, right? So if delta S is positive, and if T is always positive, what will then the value of the entire expression be? Negative. Well, and when we say the entire expression, we mean the entropy expression. So if delta S is positive, our entropy term becomes negative. And then similarly, if delta S is negative, meaning that the disorder is going down, what does the value of this then become? Positive. Okay, so guys, let's turn that then into something that we can put a finer point on. So when delta S is positive, which means the final state is more disordered, disorder is going up, negative T delta S will be negative. We just said that. And then similarly, when delta S is negative, meaning that the final state is less disordered, sorry. Somehow or another I got a parenthesis instead of a delta. That's weird. Okay, so guys, and then similarly, when delta S is negative, meaning the final state is less disordered, sorry this is so low on the screen, negative T delta S would be positive. You good on that? So guys, once you've got all of that in your notes, going back to our wildly disappointing little game we're playing, circle the one that's good. And again, the idea is circle the one that leads or indicates spontaneity. So we already circled negative delta H values and said that that was good because exothermic indicates spontaneity. Guys, what about in terms of these bottom ones? We've got these two bullets down here, the two possible scenarios, delta S being positive, delta S being negative. Top or bottom, which one is good? The top. When delta S is positive, that would seem to indicate spontaneity. So now, guys, and I think many of you are already going there mentally, mathematically, but let's make sure we're all on the right track, okay? So I'm going to switch colors and then have this thought with me. Guys, once again, are you all caught up? You're okay? Guys, which delta H values are spontaneous? Or, I'm sorry, not delta H, delta G. What Gibbs free energy values are spontaneous? Negative, right? So, guys, is that always true? If a reaction has a negative delta G, will it always be spontaneous? Are there ever any exceptions? No. You guys finally got an always. Guys, that is always. If delta G is negative, it is always spontaneous. Understand that doesn't mean it's fast. They're going to trick you that on the test. Guys, negative delta G's don't mean fast. That's a rate issue that we're going to deal with in another unit. It just means it happens. It is spontaneous. So guys, negative delta G's are always spontaneous. So now guys, let's do the math in our brain. So if this, looking now at enthalpy, we're understanding that negative delta G's are spontaneous, but relative to delta H, negative values are spontaneous, right? Because if this is negative, it increases the likelihood that this is negative. That's okay? So now let's go down here to delta S. So guys, what delta S values indicate spontaneity? Well, we said positive values, right? But how does that roll out? Well, if this is positive, this is always positive. But as we said down here, if this is positive, what's the value of the whole term? Negative. And so if this is positive, the value of this whole term is negative, again, increasing the likelihood that delta G will be negative. See how all the parts fit together? That's the idea. So guys, we're going to now apply this conceptually. Then we're going to do just a touch of math and we'll be done in about 10 minutes. So you guys good on that? All right, here we go. Switching pages, grab your books. There it is. No, you know what? I'm going to do this. Okay, so now guys, oops, I want to be able to write. Yes. Can you read that okay? That's not bad. Okay, so you can see it in your books, but we can read it as well. And I can write, and all is good. Okay, so now guys, we are ready to look at all four potential scenarios and determine whether or not these combinations of enthalpy and entropy situations changes will cause a reaction to be spontaneous. So guys, let's go through this together. If, and this is four reactions, 1, 2, 3, 4. So if we have a negative delta H, is that good or bad?
That's good.
Think about it. And again, we're saying good is spontaneous. So guys, if we have a negative delta H, is that good or is that bad? What does negative delta H mean? Exothermic. Is that good or bad? That's good. So a negative delta H leads to spontaneity. That's good. Now guys, what about a positive delta S? Is that good or bad? That is good. Entropy is going up. And then they've given us the link to the math because a positive delta S gives us a negative T delta S entropy term. So this is negative, good. This is positive, making that negative, also good. So delta G will always be negative. And what that means is that reaction is spontaneous no matter what temperature it's at. So if you've got a negative delta H and a positive delta S, that reaction cannot be stopped. It is always spontaneous as written. You get the idea? Okay, so now guys, let's look at the other extreme. Second example, positive delta H, good or bad? Bad. That's endothermic. That doesn't lead to spontaneity. Negative delta S, good or bad? Bad. Disorders going down. So, and then we can do the math and figure out that negative T delta S is positive. But guys, enthalpy is bad, entropy is bad. So what does that tell you about this reaction? It is never spontaneous no matter what you do to temperature. But guys, what does that really tell you? It tells you that the reverse process is always spontaneous. So it doesn't mean that nothing's happening. It means the other thing is happening. The reverse. Does that make sense? Okay. So now, guys, let's split hairs. You ready? Here we go. Negative delta H, good or bad? Good. Negative delta S, good or bad? Bad. So now we need to ask the question, is this reaction spontaneous? Because we have warring influences. Enthalpy is good. That leads to spontaneity. Our entropy term is bad. That is fighting against spontaneity. So in this battle between good and bad, if we want good to reign, what do we have to do to bad? We have to decrease the influence of bad. And guys, this is the point, oh golly, sorry, just a second. This is the point where we now, oh, it went back a page. This is the point where we need to talk about temperature. So let me grab a clean page. Let me zoom again. Actually, I'll do it this way. I just wanted to zoom so that we can see the equation. Okay, so here's the idea. We are now saying that this is good and this is bad. And if we want good to prevail, we have got to decrease the influence of the bad term. And what is the bad term? The bad term is the entropy term. So guys, if the entropy term is working against good, against spontaneity, how do we make the value of this entire thing less? Cool it down. Get it? If we decrease the temperature, then the value for that term decreases. And if we can decrease the value of this term enough that it is no longer offsetting the enthalpy term, which is good, the reaction will be spontaneous. So guys, the question is this. Will this reaction, and again, with a negative delta H and a negative delta S, will this reaction be spontaneous at high temperatures or low temperatures? Low temperatures, and that's what it says right here, spontaneous at low temperatures. And guys, it is spontaneous at low temperatures because decreasing the temperature decreases the impact of the thing that's working against spontaneity, which is our entropy term. Does that make sense? Okay. Of course, what's the question we're not asking? How low does it need to go? We'll answer that in a minute. Now, guys, let's look at the other example. So now let's go, sorry, it's going to force me to zoom out again. So now, guys, let's look at our other scenario. And that's not going to work because I got to do this. And I know that you know where this is going. But the idea now is this. Enthalpy term, positive, good or bad? Bad, that's endothermic. That works against spontaneity. Entropy term, positive, good or bad? Good. So what do we need to do to make good prevail? We need good to get gooder. And our good thing is our entropy term. So if entropy is now working towards spontaneity, and if we want that to become so gooder that it allows this reaction to be spontaneous, what are we going to do to T? We're going to heat this up. So guys, this becomes spontaneous spontaneous at high temperatures because now entropy is favoring spontaneity, and consequently, the higher we heat the temperature, the more likely the reaction is to be spontaneous. Yeah?
Absolute zero is when free energy is zero. No. Absolute zero is when entropy is zero.
Absolute zero is where entropy is zero.
So, in that very last example, positive at low T. So if we have a T of 1,
No, our last example, so be careful with positive. Let's do this, spontaneous at high temperatures. So this reaction will be spontaneous at high temperatures. Is that okay? Okay. You guys okay? Okay.
That's going to be specifically anytime T delta S is a larger absolute value than the negative than delta H.
Only if your delta S is positive. If your delta S is negative, it would be the inverse of that, right? Okay. So now, guys, we've got to ask and answer the last question. At what temperature does this reaction become spontaneous? So, guys, we understand that there's a tripping point. For every reaction, there is a temperature at which it will become spontaneous. Now, guys, this is critical. Understand that it doesn't always mean at temperatures higher than that it will be spontaneous, right? So if we can find the temperature of the tripping point for these reactions, it will be above that. For these reactions, it will be below that. So guys, this problem-solving process becomes a two-step process. One, you've got to find T, which determines that tripping point temperature, but then you've got to intelligently analyze based upon the signs of delta T, or I'm sorry, delta H and delta S, on which side of that temperature it's spontaneous. So guys, how does the logic work? How do you know if it's above or below? Well, you've got to figure out which one of these factors is working for spontaneity and which one of these factors is working against spontaneity, as we did right there. The question is this: how do you come up with T? How do you know the temperature at which a reaction is spontaneous or becomes spontaneous? Well, there's some math to do, right? And of course, the math is all going to be based in this, because here's our T. But guys, how can you find the T at which a reaction becomes spontaneous? Tell me more.
So you said G equal to 0.
Okay.
Your entropy turnover divide entropy by.
So tell us more about that important first thought. Why would we set G equal to 0?
Because that's going to be the point at which the reaction, so when G is negative, then it will be spontaneous.
Okay.
Positive, it will be non-spontaneous.
And what happens when it is 0?
So when it's 0, then it just doesn't happen.
No, be careful. It's not that it doesn't happen. What happens at 0? It's at equilibrium. And guys, understand that. When delta G is 0, it's not that nothing's happening. It's that they're both happening spontaneously. So they're going in both directions spontaneously. But what does that look like? Like nothing's happening, right? Because they are doing and undoing themselves at the same rate. So the net change is 0, but be careful about saying nothing's happening, because really what's happening is everything's happening, and it looks like nothing's happening because they're canceling each other out. Is that okay? Okay, but that's exactly what you're going to do. Guys, you are going to set your equation equal to 0, and then you're going to solve for T. You'll need delta H and delta S numbers. You will solve for T, and T gives you the point at which the reaction is at equilibrium. Just a second. Then once you've identified that temperature at which it is at equilibrium, then you will determine above and below based upon the relative signs of delta H and delta S, and that will tell you above or below. But guys, the trick is this. Say that we have a reaction and say that delta H is negative, say that delta S is positive. We set this equal to 0. We find out that T is equal to 150 Kelvin. Okay? So let's answer the question. If delta H and delta S are negative, and if we set G equal to 0 and solve for T and get 150 Kelvin, what would the answer to the question be? At what temperatures is this reaction spontaneous? Is it above or below? Well, let's look. Is negative delta H good or bad? That's good. What about negative delta S? Bad. So we want to decrease the influence of bad, which means we want to cool this thing down because entropy is bad. So that means relative to the temperature 150, it's going to be below. But which one of these then is right? Is it temperature less than 150 Kelvin, or is it temperature less than or equal to 150 Kelvin? Top or bottom? Just the top. It's not equal to, because what happens at equal to? It's at equilibrium. Do you get the idea? Okay. Now what about this? Will you ever solve these scenarios for these two guys? No, because that's an always never. If you've got a negative delta H, positive delta S, that's always spontaneous. If you've got positive and negative, it's never spontaneous. So the places where you'll be solving these is where you've got competing factors. You guys good? So guys, we're done as soon as we answer questions. Yeah?
So that's where you said delta G, but there are no different responsibilities.
Correct.
So if delta G is more negative, and as it gets more negative, would you say it's more likely to be spontaneous? It's not.
No, we don't use, what are those words called that are like bigger? They're superlatives. We don't use superlatives in this. We say it is or it ain't. Yeah, we don't use those descriptors. Yeah.
Is there any correlation between rate and amount of free energy?
Not for what we need to do. Rate and free energy change. No. Understand that as you get deeper into this, should you choose to get a chemistry degree, the answer is yeah. But the reason that that's considered is because they love to trick you on the AP test. And they will ask you, delta G is negative whatever, and then they'll say, what do you know about the rate of this reaction? The answer is nothing, because rate is not related to delta G. Yeah. And there are some, yeah, but for our purposes, we're just going to say there's no relationship between Gibbs free energy change and rate. Okay, you guys good? Okay, so holy buckets, right? Wow. So guys, you have got 40 minutes to wrap up this homework assignment. We will grade it on Thursday. Should you get done with that, if you're in the lab, you've got labs to be working on. You could get your calculations done for the heat of solution lab. You guys have plenty to do. I've got plenty to do.